In this video, we continue our discussion about how to associate regular expressions to a finite automaton. So the topic is the same that we ended up with in the previous lecture, and that is from finite automata to regular expressions. And in the last video, we had a method, an algorithmic method, to construct a regular expression to a language, to a recognizable language defined by some deterministic finite automaton. It's only that that method is quite tedious, and the regular expressions that it produces, they tend to be quite complex, also in terms of the length of the expression, but also in terms of nested iterations. And in this video, I want to go back to this topic and give you a much simpler method, also intuitively simpler, and also one that in practice tends to produce much shorter regular expressions. And in this video, I'm going to discuss about language equations, and I would like to draw your attention to the fact that I'm going to use pluses because I want to build on your intuition about what equations look like and how do they get solved. But whenever I'm writing plus for languages, what I mean is union, and I'm hoping that you are not going to be confused about this. And so the main tool I'm going to use in this lecture is the so-called Arden's lemma. And really, Arden's lemma is about language equations. And what it says is really the following thing. The equation, or I should say the language equation, x equals xq plus p, with p and q recognizable languages, and also this is very important that the empty word is not a part of q. So this equation has a unique solution. And in fact, that solution is PQ star. And obviously, because P and Q are recognizable languages, then obviously this is also a recognizable language. So this equation, and the main point of the lemma is, this equation, under these conditions, has a unique solution, and that solution is PQ star. So it's very, very easy to calculate this solution. So I want to prove this result for you. And I will say, first of all, I mean, the equation does have a solution. So this is certainly an equation with solutions, so does have PQ star as a solution. So we are not talking about the empty set of solutions, but there is at least one solution. And you can certainly check that this equality holds. And this is just a matter of associativity in this equation. Remember, this plus means union here. So that's the first point I want to make. The other point is I want to show that, in fact, this set of solutions really does have just one single element. So I'm going to say let X be a solution. And I would say we prove that X is equal to PQ star. So I'm going to first prove this inclusion, and I will say let U be an element of X, and let's denote the length of this word by n, n greater than or equal to 0. Remember, this X is an equation, so it's a solution of this equation, xq plus p. And let me just again replace x with xq plus p in here. So I only did this observation that x is equal to xq plus p. So what I have now is this is equal to xq squared plus pq plus p. And again, I'm using the same argument. This is equals to xq plus p. And again, I have xq plus p, q squared plus pq plus p. And this is equal to xq cubed plus pq squared plus pq plus p. And I can iterate this argument, and eventually I'm going to get to this being equal to xq to power n plus 1 plus pq to power n plus pq to power n minus 1 plus all the way plus p. And here is where it's really crucial to have this condition satisfied. Epsilon not being a part of Q, this implies that for all words of Q, the length of alpha is greater than or equal to 1. And so what this means is that it also means that for all beta from q to power n, the length of beta is at least n for all n greater than or equal to 1. So just based on this argument, because the length of my word is n, then really I have on this part of the word, so all these words here, they are of length at least n plus 1, because I have q to power n plus 1. So our u cannot be, so let me just write here, so u is in x, and x we have just established that is this much. It's xq n plus 1 plus pqn plus pqn minus 1 plus p. And the length of all these words in here is at least n plus 1. And so u cannot be a part of this. So what this means is that u belongs to one of these, so to this union, pqn minus 1, so to one of these, and this is certainly included into pq star. So that proves this this inclusion in here. So again, the key word in this part of the argument is that epsilon is not part of q. So q really consists of words of length 1 or more, which means that here when I'm iterating this q to power n plus 1, all the words in here have length n plus 1 or more. So our u cannot be in this part of the union. It's got to be in this part, and that's certainly a subset of pq star. And so the other inclusion, it's really like this. Remember that x is of the form xq plus p. So what this implies right away is that p is included into x. And this also implies that since p is included into x, and since xq is always included into x, out of these two we also get that pq is included into x. And again, I'm iterating this argument. Again, I'm using the fact that xq is included into x, and I'm concluding based on this that pq squared is included into x. And so I just iterate this argument, and by induction, I can just easily now form the argument that pq to power n is included into x for all n greater than or equal to 0. And so that implies in particular that pq star is included into x. And that concludes our result. So again, just to have it on this whiteboard, what we have proved is that if we have a language equation of the form x equals xq plus p, and PQ are recognizable languages, and the empty word is not part of Q. And this implies right away that X has got to be equal to PQ star as a language abbreviation. So this is the main result we managed to prove, and that we are going to use to discuss about the regular expressions associated to a finite automaton. So here is how we do it. We will have an automaton. Let's denote this by A, and it has a number of states. This is the input alphabet. I'm going to choose for myself a deterministic automaton, so given by a transition function, and I have the initial state and the final states. And I'm going to say the following thing. I will say for each P in Q, and I make a different discussion about Q0, not much different, but a little bit. So for each P in Q, associate the recognizable language capital P recognized by automaton, and the automaton is going to be pretty much the same as the one we had before, except that the only change we have, so we start from Q0, and the only change we have is that we say, well, what if P was the final state? And as a matter of fact, I'm going to just get rid of this. It's the same discussion for Q0. The special thing about Q0 comes in a moment. So again, for each state of P, I'm going to associate a recognizable language, which is given by the automaton that behaves exactly as the original one, except that P is the only final state. So in other words, what P has, so P is a set of all words over sigma star, such that computations or the computation of A on U ends in state P. Right. So that's what we have. And now we have to think about what are exactly these languages. How can you describe them? So here is the thing. If you have for each P, here is where I want to have a separate discussion for the initial state. So for each P, somewhat other than the initial state. So I'm thinking about these computations that end in P. I mean, to end in P, you must have had one step before you got here. That's why it's important to discuss separately the case of Q0. And let's think about the incoming transitions into state P. So this may have been from some state, P1, and maybe this was from a state PM. And this was with some, let's say, some letter AI1, and this was with some letter AIM. And all these are all the incoming transitions into state P. So if that's the case, I mean, the words that have computations ending up in P really have got to be of this structure. These are words that end up in P1 followed by letter AI1. And all these other cases, for example, here, all the words ending in PM and followed by this letter AIM. So essentially what I'm saying is the language P, if these are all the transitions, is going to be made of exactly these languages. It's the language of words ending in P1, which is described by this language, followed by this letter AI1 plus PM AIM. And really, you write all of these equations, and you can write them directly by inspecting the automaton. So there is nothing difficult about this. And you are going to solve this. So solve these equations with Arden's lemma. Let me just write the equation also for Q0. So for Q0, exactly the same equation, but you are also add an extra term. And the extra term you add is going to be plus this one. And that's because Q0, so these are all the words that have computations ending in state Q0. So by default, you could also have the empty computation, meaning no, you take no steps. And that's fine if Q0 is the final state. So just to this equation, you are adding this term plus the empty word, because you can accept the empty word if Q0 is your final state. So once you write these equations, solve them by Arden's lemma. And what I mean by this is you are going to, for example, look at this equation. If it so happens that variable P doesn't appear on the right-hand side, then you have it. I mean, there is nothing to solve. You already have the solution for P, and you are going to use this solution in all the other equations where P occurs. So this is about eliminating variable P. If P, however, appears on the right-hand side, meaning you had some self-loops in your automaton, then you just apply Arden's lemma, and you are going to get the form of P. And again, it's about removing variable P with this solution you found with Arden's lemma. So one way or another, you are going to solve each equation one by one. You replace the solution in the other equations, and eventually you get the form for all of your languages. And so at the end, what you have is that the language of the automaton is going to be simply, I'm writing as a sum, just continuing to think about these pluses in here, but really in reality these are languages, these are sets, so that's a union in here, but I continue writing it equation style. So this is going to be a sum, obviously, by all the states that are final of these languages that you have associated to F. And I realize that my notation now is not great, because you have, let me just write it like this. It's P corresponding to F. So all these languages that you have associated to the final states. I'm going to show an example, and hopefully this is going to be clear how to do this in practice. And so because all of these are recognizable languages by Arden's lemma, or regular languages, as we have seen in the previous lecture, that's going to give you a regular language right away, and a regular expression describing the structure of this language. And I hope that these explanations make sense on this abstract level, but I think that they will become even clearer once I take 2 examples. And here is my first example. This is our running example that we have used already several times, and it's going to be, and by the way, this Arden's lemma can be applied not just to deterministic automata, but it can in fact be applied even to non-deterministic automata. And I'm going to give you an example right away applying this to non-deterministic automata. And I'm going to take the language, so the language of all binary words having 1 on the third position from the right. And this is something we have explored several times before. And remember, we had a non-deterministic automaton, and that was you wait here with 0 and 1, and this is Q1, this is Q2, and this is Q3. And Q3 is the final state. And so the way you do this with Arden's lemma is you associate a language to this state, and you will say Q3. So these are the words whose computations end in this state. So you can only end in this state if you already got somehow to Q2. So these are all the words that have computations ending in Q2, followed by one additional letter that can be either 0 or 1. And then for Q2, you realize that these are, the words having computations ending in Q2 are exactly the words that first have to get to Q1, and then you have one additional letter, so it's 0, 1. And then Q1, these are exactly the words that have computations ending in Q0, followed by one more letter that has to be 1. And for Q0, to get to Q0, you must have been in Q0 in the previous step. So these are words whose computation led them to Q0, followed by 0, 1. And remember, for Q0, if you want to have computations ending in Q0, you could also just do nothing, have an empty computation, meaning you are accepting also the empty word. So here is how you solve this. For this equation, there is let me just start from this equation. So this implies right away by Arden's lemma that Q0 is, remember, PQ star. So that means epsilon times 0, 1 star, and that's obviously just 0, 1 star. And just to check intuitively, obviously, if you only want to see words getting to Q0, that means that it's just this part of the automaton, and obviously you cannot do anything else than just take any sequence of zeros and ones. So 0, 1 star is fine. And then in here you already had this solved. There was nothing really to solve. So Q1 is just Q0 times 1. So it's going to be Q1 is 0, 1 star times 1. And from this one you have Q2 is Q1, which was this one. So Q2 is this part, 0, 1 star, followed by 1, and followed by this 0, 1. And finally, Q3 is just Q2, which is this one, followed by 0, 1. So you have 0, 1 star, followed by 1, followed by 0, 1, and followed again by 0, 1. And that's it. Now you have that the language of the automaton is, this is the only final state, so it's really just Q3. And that's exactly what we wrote in there. So in this way you get the regular expression form for this language. So in other words, the regular expression you get is 0 plus 1 star, 1, 0 plus 1, and 0 plus 1. So it comes directly from this one. In this example, it served us quite well through several of the lectures. In this case, it might give you the wrong impression that there is nothing really much to solve. There is only one application of Arden's lemma in here. So let me give you another example that might give you a better impression. There are often several instances of Arden's lemma that you have to apply. And so let me take this example. So I'm going to write here the automaton. So if I have an automaton starting in state S, and this is my initial state, and it also happens to be a final state. And I go with 1 to some state A, and from state A, I go with 1 to some state B, and with 0, I go to some state C. And here in S, I also have a transition with 0 to C. And in B, I have a self loop on 0 and 1. And on C, I have a self loop with 0 on C, and I have a 1 going back to A. And this also happens to be a final state. So if I take this automaton and let's see how we get the regular expression associated to the language of this automaton using Arden's lemma. So I start from S. So S, if I think about the incoming transitions, there are no incoming transitions. So in that sense, S is really easy. It's only because S is the initial state, I have this extra term. So it consists only of the empty word. Then I have A. And A, now I'm thinking again about the incoming transition. So this is going to be S times 1, because I have this transition. These are words that end in S followed by letter 1, but these are also words ending in C and followed by letter 1. And then I have B. These are words coming from A and having a letter 1 at the end. So this is going to be A times 1. But these are also words that were already in B in the previous steps and previous step. And then you have one more letter that can be either 0 or 1. And then finally C, I'm looking again at the incoming transitions, and I have 1 incoming here, 1 incoming, and 1 here. So this is going to be S times 0 plus A times 0 and plus C times 0. So these are all the equations you have got to solve. And so S is already clear from this equation, and then what we do is I'm coming into this equation, and I conclude that A is really C times 1 plus 1, and this 1 is really the result of this concatenation. Then I take this A and I'm putting it into this equation for B. So I'm going to have that B. Let me just I can maybe yeah, I can do this either way, but let me just do it in the following way. So I will apply, in fact, Arden's lemma here, and it has the required form, so it's B times something plus this whole language. So by Arden's lemma, what I get is that B is of the form A times 1, which is this free term, times the star of this language, so 0, 1 star. And I can even now replace A to be this one. So it's going to be maybe I can just write it directly. So it's going to be C times 1 times 1 times 0, 1 star plus 1, 1, 0, 1 star. And I can just rewrite this to be C times 1, 1 followed by 0, 1 star plus 1, 1 followed by 0, 1 star. So that's B here. And for C also, first I'm going to just replace A in this equation. So I'm going to rewrite this equation to be C equals S times 0 is just 0 plus, and instead of A, I'm going to write this. So it's C times 1 plus 1. So that was A from this equation, times 0 plus C times 0. And this is now equal to 0 plus C times 1, 0 plus 1, 0 plus C times 0. So this is the same as having C times 1, 0 and 0 plus the set consisting of 0 and 1, 0. So now I can apply Hutton's lemma, and I'm going to get that C is equal to, and I have this free term 0, 1, 0 times the star of this, so 0, 1, 0 star, which is this. So now once I have C, then I can just go back and think about the language of this automaton. And the final states were S and C. So this is really made of C and S and C, which is the empty word plus this set. And obviously, this is exactly 0, 1, 0 star.